Hello, welcome you all for this introductory lecture on design and analysis of algorithms. To begin with, let us first understand one thing, that as a prerequisite for this course, you must have some basic understanding of data structures. You must have some understanding of how to write basic algorithms, and it would be preferable if you have some basic knowledge of any programming language like C, C++, Java, or in fact any programming language. And therefore, as a prerequisite to this course, we must do a course on data structures before taking up this particular subject. So, let us begin this subject. Now, as you can see, there are two important terms you can see in the definition of this subject. One is your design and other is the analysis part of the algorithms. So, let us first understand both the things more clearly, so that we can understand what are the importance or what is the significance of these two terms. The first is the design of the algorithms, designing of the algorithms. Now, design means you must have a problem first, that you need to have a solution. You are looking for a solution, you are looking for a computational solution to this problem. Now, in order to provide a computational solution to such a problem, you need to first develop a logic on paper, and ideally we say that we need to develop an algorithm for this particular problem. And when you design an algorithm, that is the first step towards this particular subject. Now, in order to design the algorithm, there can be more than one ways, there can be more than one methods of designing such algorithms. We normally call them as design techniques of the algorithms. There are in fact many design techniques of the algorithm. Few of them which you would be covering this subject is you can have a dynamic programming approach, you would be studying the divide and conquer approach, you would be studying the greedy approach, you would be studying the backtracking approach. In fact, there are a number of other techniques that you would be going through this particular course. Now, once you have designed your algorithm, right, using any specific design strategies, in fact, you would notice one thing while designing the algorithms and while developing such algorithms, that your problem is more suited to a specific kind of design strategies. It would never happen that you are able to write efficiently the solution of your problem using an algorithm with all the design techniques. Some or the other design techniques would be more suited to your problem, right. It may happen that your problem may be suited to a divide and conquer approach more as compared to your brute force method, or your design technique may be, some backtracking technique may be more suitable to your problem. With the course of the time, you would understand this aspect much better, that what these design techniques are. Now, once you design this algorithm, the next aspect of the algorithm is the analysis part. Now, once you have designed the algorithm, definitely you would like to know whether this algorithm is feasible enough for further implementation, because the ultimate goal of ours is, in order to solve this problem, is that I should be able to code this problem efficiently, I should be able to execute my problem using some programming language. So, you need to understand whether I would be able to convert this algorithm very efficiently once it would be converted into code. My programmer must be able to convert my logic very easily into some programming language. In fact, when we talk about analysis part, the basic objective of any kind of analysis is to understand that how good or what would be the performance of my algorithms, or what would be the resources, what would be the computing resources that would be required by my algorithm once it gets implemented. Definitely, one way out is that you implement the algorithm first and then understand what are the resources, what is the exact time, what is the exact memory and other resources which are required by the algorithm. And the other aspect could be that you predict, or in fact you estimate these kind of resources before the actual implementation, and that is what we actually do in the analysis part. We do not implement the algorithm first and then we understand what is the resources. So, we normally do a kind of theoretical estimation before the actual implementation of my algorithm. Very obvious, when we would talk about these aspects, when we would be talking about these computing resources, we would be focusing primarily on two major aspects of the algorithm. One is the time, and other is the space complexity or the memory requirements of my algorithm, because these are the two major concerns, would remain always a major concern for my algorithm. Definitely, whenever we would be analyzing the algorithms, we can only analyze the correct algorithms. Unless the algorithm is correct, there is no point of doing any kind of analysis. Now, let us first understand two basic terms before we proceed further. One is the priori analysis and other is your posteriori analysis. These are two aspects of two ways in fact of designing the algorithms. Now, the priori analysis actually talks about the analysis of the algorithm prior to the implementation. That means, at the algorithm level, you have not done any kind of implementation. On the other hand, the posteriori analysis talks about the actual implementation, analysis after the actual implementation. Once we implement the algorithm, and then we do analyze in what form or in what manner my algorithm is performing, right. So, definitely in priori analysis we are talking at what level? We are talking at the algorithm level, and in the posteriori analysis we are talking at the program level, right. The priori analysis is basically a theoretical estimation, because we have not done the implementation part, we are still at the algorithm level. So, I do not know what would be the environment, what would be the hardware. So, it is done at the theoretical level. I cannot understand or I cannot do any kind of calculations in terms of what would be the actual time and what would be the actual memory requirement of my algorithm. So, it is basically a theoretical estimation. We do apply some kind of mathematical models that we would be undergoing to study, right. Whereas, this posteriori analysis is all about your experimental work. Since you have implemented the algorithm, so you have that kind of benefit to understand what is the actual running time of the algorithm. You can calculate what is the actual amount of memory which is being required by my algorithms, right. So, it is very obvious that when we talk of the priori analysis, it is basically hardware independent, right, because when designing the algorithms or writing the algorithms, I do not take into consideration what would be my hardware. I do not take into consideration what would be my processor, what would be my operating system, what would be the compiler. So, all these aspects are absolutely ignored. So, it is basically called hardware independent aspect. On the other hand, definitely the posteriori analysis is what? It is absolutely hardware dependent. It takes care of the entire environment into consideration. It takes care of what would be the operating system, what would be the compiler. So, every environment comes under the consideration while doing the posteriori analysis, right. And very obvious, the priori analysis would also be language independent. While designing the algorithms or writing the algorithms, I would not talk about what would be the programming language that I would be implementing my algorithms. That concern is again ignored absolutely, and posteriori analysis definitely would be only possible because you need to convert your algorithm into a program using some or the other programming language. So, therefore, it is what? Language dependent. In the priori analysis, we actually talk about we study the rate of growth of the algorithms. Rate of the growth of the algorithms means that in what manner my algorithm would grow with respect to the input size of the algorithm. How my algorithm is going to behave or how my algorithm is going to grow with respect to the increasing size of the input to the algorithm. And that gives me much clear indication about the performance of my algorithm. That gives me some insight about how my algorithm is going to behave on my real machines. We will understand that part as we go along. On the other hand, in the case of posteriori analysis, it is absolutely experimental in nature, and therefore, we actually do a kind of calculation in terms of what is the exact running time, what is the actual memory requirements. So, we do not do any kind of theoretical analysis, we do absolutely the practical consideration part is involved. There is one more important thing that we must understand with the priori and the posteriori analysis, and that is that both these kind of analysis can be always misleading, right. Like for example, in case of priori analysis, after doing the kind of all kind of analysis, after doing the priori analysis, I may conclude that my algorithm is performing what? Linear in nature. My algorithm is behaving what? In linear nature. That means, what I say this, that I may come to a conclusion that as the input size increases, my algorithm behaves what? In a linear fashion. Now, it may happen that after the say this was prior to the implementation. This is what I have concluded after applying the priori analysis. How do we do so? That we would understand afterwards, right? So, after doing the priori analysis, I have concluded that my algorithm is going to behave in linear fashion. It may happen that after the actual implementation, my algorithm may behave in a different manner. My algorithm may have a different kind of analysis and the behavior may differ. So, in that case, this becomes what? A kind of misleading factor, right. So, definitely the prime objective of any kind of such priori analysis is that if I predicted my behavior of the algorithm is linear, so after the actual implementation also that behavior should be linear in nature, right. The constants may vary here and there, but the behavior should not change. That is one of the primary objectives of such kind of analysis. Now, similarly, your posteriori analysis can also be misleading at times. In what sense? For example, I may conclude that after doing the posteriori analysis that my algorithm is working excellent. It has excellent time complexity. It is performing quite well on in terms of memory as well as in terms of time. But it may happen that when I take my algorithm to a specific network, or if I consider that I have taken my algorithms to a kind of specific kind of environment, distributed environment or any kind of internet environment, at that point of time my algorithm does not behave better, my algorithm does not perform well. So, in that case also the entire analysis of ours may be correct, but it is misleading in the sense that I was considering my algorithm to be a perfect one, but it was not able to behave properly on the network, it was not able to behave properly on the specific kind of environment. It may not use the data very well, right. So, there could be cases where I may declare after doing the analysis that my algorithm is good enough or my algorithm is working quite fine, but it may not perform that well when it comes to some kind of specific environments. We will come to that point afterwards. Now, let us also understand some requirements and the prerequisites or the objectives of these algorithm analysis. Definitely, before I can do, see, I have already told that the priori analysis, we would be mostly talking in terms of priori analysis in the entire course of this subject, right. Because for doing the posteriori analysis, that requires implementation, and you can always, once you do the priori analysis, you can always do the posteriori analysis very easily. Now, in order to apply any kind of analysis, and that to theoretical in nature, right, because I have not implemented the algorithm, I need to have some kind of model, I need to have some kind of paper model, or I need to have some kind of mathematical model on the top of which I can apply my algorithm, and after applying that algorithm I must be able to say with some kind of justification or with some kind of assurance that yes, this is how my algorithm is going to behave on my real machines. So, I need a model, I need a base model where I can execute my algorithm, and that model would be always what? It has to be very similar to, or it has to be near to your actual implementation environment, because if the model is behaving in different manner and if the actual environment is, there is a lot of difference between the two factors, then definitely whatever the analysis part would say would not be too justified after the implementation. So, there has to be some kind of similarity between your actual implementation environment, and there has to be some similarity with that how you lay down this particular model, right. So, having some mathematical model is one of the prime objective or one of the prime requirement of the analysis part. We will be talking about one such models in the next slide. And most of the time, as we have already discussed, that we would be talking in terms of time and the space, that is the memory requirements. Although there are many other factors, there might be other factors on which the algorithms does depend, but primarily we would be taking care of the time and memory requirements of the algorithms. There could be other resources, like there could be the network could be one of the resources where I must be interested in while analyzing the algorithms. There could be how my algorithm is utilizing my data portion, that might be a point of interest, but primarily we would be talking in most of the cases the time and memory space, and specifically time would be the more important factor. So, definitely as I have told that the prime objective or requirement would be that I must have a clear understanding after doing the priori analysis that how well or in what manner my algorithm is going to behave on real machines. Definitely there would be many other factors that I have to ignore, since I am doing the priori analysis. So, definitely the hardware factor would automatically get ignored, but at the same time I need to understand that how my algorithm is going to behave on my real machines to some extent. Definitely that cannot be a mapping, because we have already ignored the major factors, that is the hardware environment and the language, all those factors are ignored. But I must get some kind of insight about what could be the possible performance, what could be the possible growth of my algorithms with respect to the input size on real machines. That is what is the basic purpose of these algorithms, right. And definitely one of the basic objectives of the algorithm is that we need to design more and more efficient algorithms. See, unless I do any kind of analysis, I would not be able to tell something about the efficiency of the algorithms. So, unless I am able to compare my algorithms, unless I am able to design the algorithms, more efficient algorithms, the entire objectivity fails. So, that would be the one of the major objectives or the major requirements of any kind of analysis. I should be able to compare the algorithms, I should be able to design better algorithms, and that is how, if you have noticed that even for a sorting example, there are so many kinds of algorithms that exist in the literature. And the reason is simply because we keep on improving the algorithms, we keep on analyzing the algorithms, we keep on doing the analysis part, and we keep on improving the algorithms, their performance, and that is how the algorithms evolve, and that is how for the same kind of problem you have what more than one kind of algorithms, right. Now, as I have already discussed in the previous slide, that we need some kind of mathematical model. Now, here in this course we would be talking about one of the most popular model of the implementation, which is actually called the RAM model, that is called the random access model. This is in fact the most popular model for implementation of my algorithms on the priori analysis basis. Definitely this model is based on some kind of assumptions, and these assumptions, although are not practically true, but they are very near to the actual environment, the actual programming environment, the actual implementation environment. Now, let us first discuss some of the assumptions. In fact, any kind of mathematical model that we would be using for the analysis would be based on some assumptions, and RAM model is also based on certain very simplistic kind of assumptions. So, let us first understand what are these assumptions. Now, in RAM model, it assumes that all the instructions, whatever kind of instruction it is, whether it is a simple arithmetic operation, whether it is a simple if statement, any kind of statement that we know or that we talk about in algorithms, all the statements, all the instructions would be counted as a simple instruction, right, and they would not take more than, and they would exactly take what, 1 unit of time step of the entire part, right. So, similarly, the loops and subroutines will not be considered as simple operations, rather they would considered as what, a group of simple operations. So, when we talk about loops, so there are more than one statements which gets executed in loop, as we all know. So, actually loop would be nothing but a combination of simple statements, right. There is one more assumption which is out of the which is very different from the actual environment, or which is not true in terms of practical environment, and that is that in RAM model we consider that every memory access will take a same amount of time, or it will take us exactly 1 unit of time stamp, which is not true practically, because as we all know, if we must have studied the memory hierarchy, we are all aware of that the memory access depends upon the location of your data portion. If your data is available in secondary storage memory, then memory access would be great, right. If my data portion is available in the cache memory, then memory access would be very short. So, the location of the data portion is important when we talk about the memory access. This distinction or this practical scenario is removed or absolutely ignored while doing this kind of analysis in RAM model. And reason is very simple, we have to make the things simplistic, we have to make things, otherwise it would be very difficult while designing the algorithms. I have to always talk in terms of where my data is, and based on that things would become too complex. So, in order to maintain the simplicity, we assume that there is no memory hierarchy, all the data at all kind of memory access would be similar in nature. So, that makes things much simpler for me for doing the analysis. Now, definitely in order to apply any kind of mathematical model on my for the analysis part, we need to convert my algorithm into a suitable form, right. I need to, since we are talking about that we would be applying the mathematical form or mathematical model on my algorithms. So, there has to be some specific format in which I need to convert my algorithms, because having an algorithm and then in terms of number of steps or number of instructions, it would be very difficult to analyze, right. So, there is one method that we normally use for doing such kind of analysis, and that is called the step count method, or we normally also call it as a frequency count method. Now, let us first understand what exactly this method is all about and how and what actually we are trying to do. Now, in this method, if you can note, if you can understand this, we can list my algorithm and we can name all the steps of the algorithms 1, 2, 3, right, as we have already done. This is a very simple algorithm where what we are trying to do is we are trying to sum all the elements within the array, right. So, what we will be doing is, why it is called step count method, because we would be talking in terms of what would be the number of steps or what would be the count of each and every step of my algorithm. So, I will be listing 3 columns. One is the statement cost, where we would be talking in terms of what would be the cost of each and every individual statement in my algorithm, right. Then we would be talking in terms of frequency count of my algorithms, that is what is the frequency and how many times that particular statement gets executed, that is important. There could be case when the algorithm might take a constant amount of time, and there could be the case when this constant amount of time may be executed n times, right. So, I have to include that frequency also. So, the second column would be talking in terms of what is the frequency of each and every statement, which I have listed in the first column. And then there would be a total, which would be nothing but the statement cost into frequency would make you the total cost, right. So, let us take this example and understand some minute things. If you can see very carefully that what we have done is we have taken the statement cost of the definition of my algorithm as 0. Normally what we do is we would only count the logical part of my algorithm, right, the steps which are executable, although all the steps are executable, but we would only take care of only those statements which acquires or which are doing some kind of calculation, which is doing some kind of step executions, right. So, we would be normally ignoring the definition of the algorithms, right. We would be considering them to be a statement cost of 0. We would be ignoring your the start and the end of the end statements of the algorithms. So, here we would be only talking about what statement 3, 4, 5 and 6. These would be counting in terms of the execution of my algorithms, that would actually is building up the logic of the algorithm. So, the first line would be taken as a statement cost of 0, and therefore, the frequency is also 0, and therefore, the multiplication of these 2 terms gives me the total cost of 0, and similar is the case for the starting curly brace, again the total cost is 0. Now, if you take understand this point, s is equal to 0, this is a single assignment statement, and in the entire life cycle of my algorithm, this statement would be executed only once, isn't it. So, the statement cost would be 1, that is, say we have already assumed by a RAM model that every statement or every instruction would not take more than 1 time step, right. So, all the instructions will not take more than 1 time step, that is for sure. So, the statement cost would be as individual statement, it would be 1, and since the entire life cycle of the algorithm, it would be executed only once. So, therefore, the frequency comes out to be 1 here, right, and therefore, the multiplication of these 2 terms comes out to be 1. Now, next is your for loop statement. If you see carefully, as we all know that this for loop is getting executed from where? It is getting executed from 0 to your n minus of 1 time. So, which is nothing but it is total of n times, isn't it. So, that for loop gets executed n times, but if you notice I have written n plus 1, and reason is very simple, that this for loop gets executed till n minus 1, definitely that becomes n, but it would go at least nearly one time, that is when I would become n, at that point of time it would come to know that this for loop becomes false, is not it. But since that execution has already begun or has done, so therefore that additional 1 comes from that factor. So therefore this for loop would be n plus 1, right. I hope you understand this. So the statement cost would be 1, but the frequency would be n plus 1 time. Even if by mistake, or even if you are not aware of this and if you write n, that would also not make much difference, and you will come to know about this afterwards. So you can write n plus 1, and the multiplication of both the factors would give you what, n plus 1. Now the next statement, this statement which comes under the for loop. So therefore the as a single statement the cost is 1 and the frequency would be n plus 1, right, because when this for loop would additionally go n plus 1 time, but the statement which is being executed under this for loop would go only till the for loop gets executed for valid inputs, right. So it would go only for n times. So 1 into n, again n. And similarly the last statement, this return statement, as we all know, would get executed only once in the entire life cycle of the algorithm, and therefore the frequency is 1 and the statement cost is also 1, and therefore 1. And last statement I have already told. So what we do in the end, we take the sum of all these terms, and the function comes out is equal to what, 2n plus of 3. Now this 2n plus of 3, this fn is equal to 2n plus of 3 is what? It is basically nothing but it is representing the number of computations or number of steps in terms of input size n. N is what? Input size. So it is talking about what is the number of computations in my algorithms, right, and these number of computations can be indicative of very important aspects of my algorithm. By understanding these things and by doing the analysis on this part, we would be in the later slides, I will be coming to this point, that how this 2n plus 3 can be analyzed, and what important factors or what important knowledge we can get from this particular function, right. So normally what we do is we plot a graph and we understand that how my function fn. So we normally do what, the function fn, and we take n is what, input size. So we try to understand the rate of the growth of the algorithms as the input size grows, that how my function fn behaves. So that is what we would be doing in the coming slides, right. Similarly this was now if we consider this function fn in terms of time, that is how my algorithm would, because as the number of input size would increase, I can talk in terms of the time also, right, because the input increases, as the input size would increase, more number of computations would be executed, and therefore I can talk about in terms of time. And similarly if I talk in terms of that as the input size increases, what would be the usage of my memory variables or my data structures, then I can talk about what, space requirement of the algorithms. So the context becomes different. If we talk in terms of time, it would be called as time complexity. If we talk in terms of memory space, it would be called as the space complexity. For example, in space complexity, for example, here we are using what? We have to list down all the memory variables that we are using this particular algorithm. One is we are using what? The array A of size n, right? We are using n is equal to 1. This n, the size of n is what? The 1 is over here is the frequency. N has been used only once. It has been used as a placement holder, right? So the value of n whatever may be, but it would be treated as what? A single count, right? So its frequency is 1. The frequency of array A would be n. Frequency of the variable n is 1. Similarly, frequency of statement s or the variable s is 1, right? Because it has been used 1, right? And similarly, the frequency of the variable I is also 1. So we can again list down these variables, their frequency, and when we can take a sum of these different variables which have been utilized. So here we can say the space complexity, although it is a very basic level first, as you will go along you would be understanding it in more complex kind of things. But as of now this understanding is good enough for you all, that the space complexity can be listed down as what? N plus of 3. Now, it is also important to understand one thing, that step count in step is any computational unit that is independent of the problem size. Definitely, when we were doing the step count method, we didn't talk about what is the size of the input, right. So, whatever may be the size of the input, when we talk about any step, it is any computation that is absolutely independent from the problem size. For example, suppose I have 5 additions, right. If I have written 5 additions, then that can be treated as what? A single step. Even if I suppose 1000 additions, it can be treated as a single step. So, unless my step does not depend upon the input size, it would be treated as a single step. Practically it is not true, but that is how the RAM model assumes, right. So, if example, but if I have 5 additions, suppose if I have n additions where n is the problem size, then it would not be considered as what? A single step. Simply, if my steps are dependent in terms of, or have been expressed in terms of input size n, then it is different. Otherwise, if it is not dependent on the input size, then all the steps can be taken as what? A single step. All the operations done in a single expression can be taken as a single step, right. For example, in this case, if I consider n to be the input size, so in this case we have not used n in any of the part of this written statement. So, I can consider this to be a single statement, although ideally practically would not consider this as to be a true, because there are number of instructions hidden into it, but as per the RAM model, I would consider this as to be a single step. Had there been any expression in terms of n, suppose one of the variables was expressed in terms of n, in that case the scenario would have been different. That case it becomes dependent on what? Input size n. So, this is not practically absolutely true, and that is why some people do complain about the RAM model, about the suitability of the RAM model also. But that is how the RAM model has been treated as, and that is how it brings in the kind of simplicity in order to do the analysis part. Similarly, like x is equal to y would be treated as a single statement, right. So, let us if you notice what we did in the earlier slide, if we had a simple algorithm like the case we did in the earlier slide, the things seems to be okay. Suppose if there was 1000 statements, there were 1000 statements in my algorithms, then counting each and every step of the algorithm and writing and making a table listing down the frequency or listing down the count of each and every statement, it would not be feasible enough. So, we need to find some suitable and more feasible method where I need not to talk about each and every statements individually, because that is not always feasible. For smaller algorithms it can be good enough. So, there is another method apart from this step count method, which is called what? Counting the elementary operations. So, what we do here is that rather than counting each and every statement of the algorithm, we actually take care of only the basic or most elementary operation of my algorithm. The most elementary operation is what? It can be defined as what? There cannot be any other operation that can be performed more frequently as the size of the input grows. That means, a statement, that statement would be called as elementary operation which has the highest frequency of execution in the entire life cycle of my algorithm, right. And in order to identify such kind of elementary operations, we normally look for the statement which is present in the embedded loops, which is present in the loops, or which gets executed most of the time. The frequency of such statements would be maximum in the entire algorithms, right. The time to execute an elementary operation must be constant, right. The operation itself would take what? A constant amount of time. It must not increase as the input size grows, right. The operation, whatever operation which I would declare as an elementary operation, it should not depend upon the input size. It should not, the size of the operation or the number of operations must not increase as the input size increases, right. Now, let us take a very simple example to understand that how we and what operation how to identify these kind of basic operations and how do we represent these kind of basic operations, elementary operations. There is a very simple example which talks about finding the max within an array, suppose A, right. So, now what we can do is, in order to identify such kind of basic operation or elementary operation, we must first look for a loop, right. And then we must see that what is the embedded statement, most embedded statement within this for loop. So, we find that this statement can be treated as the basic operation, right. Here we can see that now the execution of this statement depends upon two major aspects, or we can talk about two major aspects of this particular statement. One is what is the maximum or what is the worst case in which, or what is the worst number of times or the maximum number of times the statement can be executed, and what is the minimum number of times this statement can be executed. So, we normally call it as a max case or the minimum case. For the max case, this would be the case for all i's if statement is true. Definitely this statement would be in the entire algorithm, this statement would get executed maximum number of times when for every value of I this if statement becomes true, right. So, in that case I would say that this max is equal to AI would be having the highest frequency or would have the highest number of executions, right. So, that would be treated as max case. For the minimum case, definitely for all I if statement is false, for every value of I within the for loop, this statement gets if statement gets false. So, in that case the max statement would be executed the minimum number of time. So, these two aspects are important while identifying the elementary operations. So, what we do is, so we ignore all of the statements, rest of the statements, and we just list down the total frequency count and the total execution or the total statement cost of your the basic operation, and we list down the total number of operations of the algorithm in terms of the total number of computations which would be done for the basic operation, and rest of the things can be ignored, right. Let us take another example to understand this. Again we have a very simple example where what we are doing is we are telling whether the array contains array A, we are using the array A, we just wish to understand whether the item X is contained in the array A or not, right. So, we see very carefully. So, we have a loop. So, we must first look for a loop, and we see that what is the embedded statement into it. There can be two statements, there can be any number of statements. So, in case we find that this can be treated as the basic operation of this particular algorithm. So, what could be the case here? Now, this again what could be the maximum case? If maximum case could be the case when this for loop gets executed for the entire full length of its value, right, for the full length of this array A, whatever may be the size of the array. If it gets, suppose if the size of the array is n, so in that case the loop will go from 0 to n minus 1, that is n times. And if that could be the case, then I would say that this if statement gets executed maximum number of time. So, there could be the case when the item which I am looking for is not found within the array A. So, that could be the worst case, right. And similarly, there could be a case when I am able to find the element X in the first position of my array, right. If I am able to find the element in the first position itself, that could be the case when my execution of this statement executes minimum number of times. So, by understanding the basic operation or the elementary operation, I can talk in terms of the entire analysis of the algorithms. I need not to talk about other statements, I can definitely ignore rest of the statements. We will take another example, this time we will take embedded loop. Suppose we have double loop, right. So, we have one loop beginning with I, and we have another loop in variable j, right. So, if we talk about the frequency of this statement, right, this for loop gets executed suppose n times, again this for loop also gets n time. So, if we find that this could be treated as the basic or the elementary operation of this particular algorithm. So, in this case definitely a contribution from the first loop would be n, and the contribution from the second loop would be again n. So, here we can say that this particular statement gets executed n squared times, n into n times. So, this is how we can look for a basic operation within my algorithm, and we can talk in terms of what could be the possible number of operations, because see if we would have done it the way we were doing for the earlier case, that is if we would be listing each and every step. So, what could be the only difference? It could have been the case that I am getting 2n square plus 1 or 4, suppose I am just taking example. So, what we are getting in that case, the only difference would have been these kind of constants would have been additional constants which I must have got, I would have got when we were doing what, each and every statement would have been taken into consideration. And when we take care of only the basic operations, these constants may differ or may get ignored, but the major portion is what, this n square. This is the the complexity of my algorithm, right. So this term gets counted, right. We must not be able to ignore these kind of major terms, which is expressed in terms of n, right. So that is more important. So with the when we would be doing the presentation on the asymptotic analysis, then you would come to know that these constants do not carry a lot of weightage. We can always ignore these constants, right. Again, one of the simple examples I have given here. So in this case also, if you see, it's a while loop, right. So the basic operation, we can list down this to be the basic operation, where the execution of this would depend upon the while loop, whether the while loop would execute how many number of times. So we can always talk about the basic operation depending upon how my loop, or what would be the frequency of my statements. I have listed a very simple assignments, right. Whatever we have done, you can go through these assignments and try to apply what the understanding that we have learned from today's lesson, right. So I'll suggest you to do these assignments. These are important assignments, and if you have any kind of, I've listed few references also. I'll suggest you to go for this book on Corman. This is one of the most fundamental books, and in fact a very important book on this subject. You all must read this particular book specifically. There are many other books. You can also read the book on this Donald Knuth, again a very important book on algorithms. So I'll suggest you, Geeks is again very important contents. There are very important good contents available for algorithms. So I'll suggest you should go for these references, or in case of any problems, or if you want to have any kind of queries, you can always get back to me, right, on this particular mail ID. Thanks a lot.